Assalamu alaikum, doctor. How are you? My name is Saif Ahmed, and this video presents the Power Distribution Lab 1. Uh, it's about distribution, load flow, and voltage profiles. So the objective was to use Python and Panda Power to analyze the IEEE 33 bus radial distribution feeder. I examined bus voltages, feeder losses, line loading, and the effect of increasing and relocating loads. So let's start with the network setup. As you can see here, I imported Panda Power for power system analysis, Pandas for tables, and also for plots. So I also loaded the IEEE 33 bus feeder using this code. This created a network containing 33 buses, 32 loads, 37 lines, and one external grid. And I also inspected the main input tables using a net bus head, net line head, and the net load head. These tables contains the bus information, line parameters, and active and reactive load values. So the total load was, as you can see here, was 3.715 megawatt for the active power, and for the reactive power it was 2.3. And for the base case power flow, uh, I used this code and I ran the power flow using these two codes. The results of the net converged was true, confirming that the power flow was solved successfully. And here for the minimum voltage was 0.913 at bus 17, and the maximum voltage was 1 at bus 0. Bus 0 is the source bus, while bus 17 is the weakest bus due to its electrical distance from the source and the accumulated line impedance. And yeah, and for the voltage profile, as you can see here, we have the graph. The graph shows the voltage at every bus. The dashed lines represents the acceptance limits of 0.95 and 1.05 PU. Several buses are below 0.95 PU, so the feeder already experienced under voltage in the base case. The lowest point occurs at bus 17. So, as you can see here, the losses and line loading. I used the line results table to calculate the total real power, the total real power losses. And as you can see here, it's 0.2 megawatt, and I converted it to kilowatt. The most heavily loaded line was line 0, connecting bus 0 to bus 1. This line is near the source, so it carries the power required by most downstream loads. So here we have the bar chart for the line loading. It confirms that the upstream line carry more current than most downstream sections. Next part will be here. Yeah. So I increased all active and reactive loads using multipliers from 0.5 to 1.75. For each case, I recorded the minimum voltage, weakest bus total losses, and the maximum line loading. As the loading increased, the minimum voltage decreased, feeder losses increased, maximum line loading increased, and bus 17 remained the weakest bus for uniform load growth. For example, at 100% loading, the minimum voltage was, as you can see here, 0.13, and at 125% was 0.88, and at 150% it was 0.86, and at 0.83 it was 175%. So we move to the plot, the minimum voltage versus loading. This plot shows that voltage decreased as loading increased. The first tested voltage violation occurred at a loading multiplier of 0.6, where the voltage becomes 0.900 something, 0.94, I think. Um, it was 0.94, something here in between. And therefore the maximum tested loading before violation was 0.55 with a minimum voltage of about 0.95. And next will be the feeder losses versus loading. The losses increased non-linearly because conductor losses are proportional to current squared. Therefore, increasing the load causes losses to grow faster than the load itself. And the next part will be this graph, which is the maximum line loading versus loading. So the maximum line loading also increased with demand, although the calculated values remained below the line thermal limits. Yeah, yeah. Here, I increased only the load connected to the last 10 buses from bus 23 to 32 by 50%. And then the results were the minimum voltage was 0.8836 pu, and the weakest bus was 32, and the total losses was 354.31 kilowatt. So this shows that load location is important where when additional demand is concentrated near the feeder end, the remote buses experience a greater voltage drop. So we move to the next challenge, which was the weak bus investigation. So bus 32 is supplied directly by line 31, which connects bus 31 to bus 32. Bus 32 became the weakest bus because it is located at the end of the feeder. The current must pass through several line sections, so resistance and reactance create cumulative voltage drops. The concentrated downstream load also increases current through the upstream path, causing an even larger voltage reduction. So we move to the planning challenge, which is here. For the planning challenge, I increased all the feeder loads uniformly by 40%. And as you can see here, the results were the minimum voltage is 0.87 pu, the critical bus was bus 17, and the critical line was line 0. The critical bus is 17, sorry, and the line is 0. And the total real power loss is 424.65 kilowatt. So the line loading remained acceptable, but the voltage was below 0.95 pu. Therefore, the feeder was not acceptable under this condition. So the main issue was under voltage rather than the thermal and overloading. So a suitable engineering solution would be to install a capacitor bank or voltage regulator near the weak downstream buses. This would provide voltage support and reduce reactive current flowing from the source. So this lab helped a lot, helped me understand how Panda Power can be used to model a radial feeder and also run power flow calculations, also adding and analyzing the voltages, losses, and line loading. So overall, the voltage support devices, feeders, reconfiguration or additional feeder supports may be required to improve the system. So that's it for my part, and thank you so much, Doctor.